Michael, very much for your invitation. And yeah, I'm very glad to share this recent work to discuss it. So when did you say Dorit talked about it?
I think in December, early December, she gave I think an overview of something that sounds related.
Okay, so I didn't know that. Sorry. So that may be a little bit repeating. I think by December we certainly had the majority of the results. Yeah, but maybe you can hear a different summary. Yeah, so this work is on arXiv, and then also you can see the talk of Jordan Kotler on QIP. And so the main motivation is to address this quite fundamental question, like what's a most general quantum physics experiment? We know like experiment is the foundation of physics. Like we all, I mean, new physics always are based on new experiments. So now we have the ideas about quantum information, quantum computing. The question is whether that change our understanding to more general, in general, what a quantum physics experiment is. And then motivated by that question, we build this general framework. And then that allows us to address questions about complexity and also study a particular example, which is several problems that are related. And I'm going to define them later, but they are motivated in physics. So as we are trying to show that quantum coherence in accessing the experimental system is essential, and that whether or not you have that will change the complexity of some task greatly. So yeah, so what is a quantum experiment? I mean, the first thing we think about is a quantum measurement, which is you take a state and then you measure it, and then the wave function collapses into one of the eigenstates of the measure operator, and then there is this probability interpretation. But in reality, we study a quantum system in much more general ways, which means like if I, instead of thinking about the double-slit experiment, instead of just measuring the state at the end, I could do some manipulations first, and then I do some measurement in the end, right? So I could first say put in some other devices and change the polarization of the photons, and then depending on that, I get different measurement results. So I could measure some kind of correlation between what I did before and what I see. So, and this can happen multiple rounds. In general, I could do some I could do some control and do some partial measurements, and then do this multiple times. And then more generally, like these are more like experiments where only the physical system is quantum, and then our lab, everything else in our lab is classical. But more generally, we could also make use of quantum systems as part of our lab equipment. For example, maybe when you're studying some photons double-slit interference, then maybe there is some other photons you bring in and entangle with it. I don't know what that can do, but I'm just giving an example that you could have this orange photon EPR pair, and then use that as your device. Right? So you can use something with quantum entanglement as your tool to probe that unknown system. So the lab, the tools you use in the lab itself could be quantum, and there could be quantum entanglement involved. And then there's a question like what can it do better than the classical experiments. So maybe it's helpful to think about this quantum extended Church-Turing thesis, which I think helps us to clarify these kind of questions. So basically, this quantum extended Church-Turing thesis says that if I have a universal quantum computer, it can efficiently simulate any physical system, just like the classical computer can simulate classical system. So we can think everything in the lab, like the whole thing here is like a quantum computing, like an algorithm that runs on a quantum computer. And then that motivates these kind of questions, like can I think of the experiment as an algorithm? And what if that is an algorithm, what is the task? Right? So like what are you designing that algorithm for? And then what's the definition of the complexity of an experiment? And then can we speed up experiments by using quantum algorithms rather than classical? So and the last one, which we will mainly focus on in the specific example, is whether there is a key, an important advantage for having a coherent access to the system. Yeah. So so in general, we can think about the experiments, like you can think about a physics experiment this way. Like you could have a classical everything, which is just like classical physics experiment, a classical lab and system. You could have a quantum lab studying classical system, which is just like using quantum computer to analyze data. If your physical system is classical, then the only thing the quantum lab can do is just analyze data better. But if you have but then the modern days condensed matter experiments, most of them are in this corner, and you have a classical lab measuring quantum system. But the most general one is this what we call QUALM, which means quantum lab and quantum system. But within that there is still a difference, because you could have like everything. You could have like the most general case where the whole thing is like a big quantum algorithm. You could also have a restricted case where you have quantum dynamics in your lab equipment, and also in the physical system you study, but they may not be able to communicate quantumly. So that maybe there is only classical communication, and an example of that is like the scanning, is like the superconducting quantum interference device, which is the SQUID. Like for example, you use a quantum effect to probe a magnetic field. So you are making use of this quantum superpositions in superconducting ring, but you are just measuring the magnetic field. So the communication between the system you study and the device is classical. So that's kind of the examples where this happens. So let's think about what's the general way that we can set up a framework for this general quantum experiments. So we can always separate the systems into three parts, and let's think about this example of the X-ray diffraction. So that's the standard experiment that you use to find out the crystal structure of a crystal. So you send in some X-ray photons, and then they reflect. They got diffracted by the crystal, and then you measure them. Right? You just take some picture. So here there is the system N, which is the crystal, that the system N that you don't directly touch, and you don't know what it is. Then, or at least there's some information in it, but you don't know, which in this case is the crystal structure. There's some hidden information there you don't know, and you want to find out. And then there's the lab system L, which is the photon here, and that's the system that you have some control. You can decide which direction you send in the photons, and that L system interact with N. And this interaction between L and N is also given by nature, and it's not what you control. But other than that, you could control how you process the data after you get L, and so on. And then everything else, you call it W, which is basically like the camera that takes the picture and so on. So they don't directly interact with N. So that's our general separation of three systems, which correspond to three independent Hilbert spaces. Oh, by the way, feel free to interrupt me anytime if you have questions. So then when we have these three systems, then we first want to define this lab oracle, which means which describes this unknown thing that we are trying to find out, like the physical system with unknown parameters. And that the lab oracle is this is a combination, is this this initial state of N, which we don't know, and this dynamics of NIL together. So this ENL is the quantum channel that describes coupling between N and L, and it also includes the dynamics of N itself. And And then usually what happens is you're given a set of lab oracles, and then your task, and what are you trying to do by this this algorithm, which we call QUALM, is that other than that gray ENL channel, there are other channels you can apply to LW, which you can control. So these are what you can do with, like, you take the photons and then couple it to something else, or take a picture of it. So these are like the blue part, the quantum circuits. That's what you have control, and the gray part you don't control. And then your task is usually finding out some properties of this unknown part. So you formulate that as a map from the lab oracles, and in general there can be other inputs from W. You want to map the lab oracles and the input to some output. So for example, in the X-ray diffraction example, you don't have the input here, and you're just mapping one of the crystal structures to a number. So you're trying to find out there is 230 different crystal structures, and then you're trying to just get that number. But we keep the input because it's possible that you're not just asking about which lab oracle you're using, but you're saying, like, if the lab oracle is L1, I do this calculation. If the lab oracle is level L4, I'm doing another calculation. So in general, it's possible to do that. And then there is another important concept that we need to include in the definition, which is admissible gates. It means that you can't you can't just say I have this task and I have these lab oracles, then I'm allowed to do anything to find out that. Okay, that you can do that, but that's not what in general happens in quantum experiments, because you're usually limited by your ability. And one example is what we are going to discuss later, that then you may not be able to communicate quantumly between L and W. Right? So there could be other kind of constraints. For example, maybe your gates are local and you are limited by how deep is the circuit depth. So so there can be different constraints, and which we put in this admissible gates. So there is a set of gates that are available to the experimentalist, and these gates are what you can introduce to make your algorithm. So then with these different parts, then we define a QUALM means a sequence, which is basically this picture on the right side. It means a particular algorithm, which means a sequence that you apply this gate and then call the lab oracle, and then apply that gate and then that gate, and then call the lab oracle, and so on. And by the way, the gates I mentioned here should be quantum channels. It doesn't have to be unitary. So okay, so then a QUALM is basically a quantum circuit with some part that's a black box that you don't know, but also there is a Hilbert space that you don't know. There is a Hilbert space N which you don't couple to, and there is a hidden state. Okay, so for as examples, we can look at what are the this is a general framework for basically any quantum experiment. So it includes many things we already know. So for example, quantum algorithm can be thought as a trivial example, which is just where you don't have the hidden part. Like you have this L system with n qubits, and then there is no n, and then you are just your task is just mapping input to output. So you're taking some so your task is classical. That's the difference between QUALM and quantum algorithm. A quantum algorithm has a classical task, and you're just trying to achieve that using the quantum circuit when you're allowed to use a universal gate set. And another example is quantum state tomography, which is when you have the state and then you need to access the state multiple times, and then you're trying to find out what state that is. So the lab oracles are basically just generating states. Like every time you call that channel, it generates a state for you, and then the state may be coming from a set, like and then you're trying to find out which state that is. So then usually you also consider a universal gate set. So of course there are also interesting generalizations. Like you could ask, what if I have some restrictions on the gate set? How does it become hard to get a quantum state tomography? So then the third example is like a generalization of this X-ray. So in this X-ray diffraction setup, you have this N is the material system, and then L are the particles you use for imaging, which could be photons or electrons or other particles like neutrons. There's a lot of different imaging techniques in condensed matter, and you send in this to couple to your system, and then but the quantum generalization could be like you can send in some entangled states of photons. And then, or you can have photons coming in, and then you can measure them in an entangled basis when they get out. So in general, that's different from the standard techniques. So these are examples that we can think as examples of QUALM. Any questions? Okay, I hope that, yeah. I hope the definition is clear. And then we are going to, so let's discuss a little bit about complexity. So as I mentioned, so the hope is that when we have this general framework, then we can quantify what we mean by complexity of an experiment. So so we just view this QUALM as a quantum circuit, and some parts are unknown. And then we can define the two different numbers. So the query complexity is the number of queries to the lab oracle. So you take the your algorithm include how many calls to lab oracle. And then the other is the gate complexity, which is how many gates you use to in between, like how many of these gates in the quantum circuit part. So the blue part has a complexity CG, and then the gray part has CQ. And then the quantum complexity, you can just sum over them. Of course, I mean, in practice, maybe they don't have the same price. I mean, maybe it's hard to call the lab oracle, and it's easier to apply your gates, or the other way around. So there may be a number that's a different weight. I mean, it's not obvious that you just sum over them with the weight 1. But I guess that doesn't affect any qualitative features. Like you're probably interested in whether each of them is growing exponentially or power law in this in a given problem. So then basically the QUALM like a task for a given task, the complexity of that task means that the QUALM that can realize it with a minimal complexity. And so if I give you a task like factorizing numbers, and then the complexity of that task is just the task of the it's just the complexity of the minimal algorithm that can achieve it. So, but the difference from quantum algorithm case is here the complexity is defined not just for a task, but for a task and admissible gates. It means that my task is to find out something hidden in the physical system, but I also need to tell you what I'm allowed to use. And then some tasks are easier if you give me universal gate sets, but they become very hard when you have a restriction. So that's here this and in particular that one kind of restriction that we are very interested in is this difference between coherent and incoherent access. So as an example, if we consider this boson-Einstein condensation, so how do you do experiments in these systems? What you usually do is you can control some parameters like magnetic field and so on. Like you can control some parameters and evolve the system. So these are like the dashed lines I draw here. Like you can introduce some controls to the dynamics, and then in the end you take a picture. And so in the end, like you release the potential, and then the atoms all fly out, and then you take a picture. That's at least one standard way I know how experiments were done. So that's an example where after you do that, the state is gone. Like you do that measurement, and then you took the picture. Next time you have to restart. Right? So this is an example of a incoherent access to the system. Like when you do the measurement, you can't like continue evolving the system coherently, and also what you learn from the system is like some classical information. So although even if you have a quantum computer in W, it's still possible that this communication is restricted to be classical. So that's so we want to formalize that difference and then define these two classes of QUALMs the coherent access QUALM basically means it's most general, like you have available universal gate sets, and there is no constraints on coherence. And the incoherent one means that the L and W are both quantum systems, but they are only having LCC between them. So so between when I apply this blue box, the quantum circuit, it's only LCC between L and W. And moreover, we have another condition which says that within these LOCCs, I mean, I draw these LOCCs into multiple rounds of measurement and control. So it's like the circles are measurements and the box are quantum channels. And so you measure L and then apply some quantum channel on W and back and forth. But we require that one of them is a complete measurement, which means that there is no coherence between the state here and the state that enters next round into the lab oracle. So you restrict the coherence in different applications of lab oracle and between L and W. And we want to study problem where these two have very different, where this restriction has a significant effect. So basically, we're going to show that there is a hierarchy. And the thing we focus on is the arrow on the left side, which means that if you restrict it from the completely coherent access, like you're still allowed to have adaptive operations. Like you're not just repeating the same measurement many times. You could do more clever things, like you measure the system and then have some back and forth communications, and then you send the signal. Then you next time you decide based on the previous results, you decide to do something else. You decide to do a different measurement, and so on. And so the key results we are going to discuss is that even that is much weaker than the coherent access. So we are going to show some exponential advantage in a particular toy problem in several different problems. And then we just want to clarify that that's different from the more well-known case of the exponential advantage, which is the Simon's algorithm. That doesn't require this kind of coherent access. It's only it's sufficient to use the linear superposition. So you don't really need a entanglement between these different parts. So maybe I will skip the more details. And so let me define this particular problem that we studied using this framework, which is this fixed unitary problem. And this is motivated by the physical question. Like I could have a deterministic system, like a Floquet system, which means you have a Hamiltonian that's time dependent, but is periodically time dependent. And then another system is a Brownian circuit, which means you have a Hamiltonian that's time dependent, but it's random, so there's no periodicity. Then in both cases, thermalization could happen. Like you could have temperature goes to infinity. Basically, in general, temperature goes to infinity, and the system just completely thermalized. So it can be hard to distinguish them. Both of them can have quantum chaos. And then, so the question is, how hard is it to distinguish these two cases? So we consider this toy model for that physical problem, which is you're trying to distinguish two lab oracles. One lab oracle LOQ, which is the one on the left side, that just every time you call it, it applies the same unitary. And the other lab oracle is every time you call it, it applies to a random unitary, and the different random unitaries are uncorrelated. So our main result is that distinguishing these two cases is very easy for coherent access, but if you don't have coherent access, it's exponentially hard. You need to call the lab oracle. You need to call the lab oracle exponential many times in order to distinguish them better than in order to really have any non-trivial way to distinguish them. So first, the simple proof is that it's easy to do that with coherence, because basically you can, if you are allowed to do anything on L and W on any case, you just do a swap gate, and that allows you to let's say I put in a reference state 0 to this system, and then it applied the lab oracle, so it got applied to a unitary. And then I do a swap, so this thing goes out, and then another qubit comes in, and then the other qubit is in the same state, 0. And then that's got applied to another unitary. So I just want to know whether these two unitaries are the same or different. So you can just do a swap test, and then that measures the overlap between the two states. If you so the swap test is a measurement that succeeds with probability 1 if you have the same unitary, and it gives you a random result if you have two different unitaries. So so that can tell apart these two different lab oracles with a order 1 number of steps. So and the main non-trivial thing, this is easy. The non-trivial thing is to show that it's hard for the incoherent access. So we proved that the main theorem we proved is that when we, if we call the lab oracle less than this exponential number, so little l is like the number of qubits in capital L. And by the way, yeah, I didn't emphasize that earlier, but in this problem, n is just the user to record the lab oracle, and so you don't really need a quantum state in n. So n is storing storage of that that qubit that tells you what unitaries you apply. So L is the size of the capital L system, and then the statement is that you have to call the lab oracle exponentially many times in little l, 2 to the L times 2/7. Before that, you can show that no matter how you try to design your algorithm, then the output state of W is always very close between these two lab oracles. They're always exponentially close before that, before you reach this exponentially many lab oracles. And I would like to provide some intuition why that's true. And you can think of a simple example of the incoherent access QUALM, which is just you're doing a complete measurement. Like every time you do a complete measurement, and you're doing the same one. So that's not a general algorithm, but it's an example. So so like every time you're basically just repeating the same measurement at k time. So you prepare some state and then apply the unitary and then and then measure it in the spaces x. So you get a probability distribution, which is different for the two cases. So in the case of the fixed unitary, like the L or Q, then this probability distribution, there is some correlation between the different measurement outputs because you're applying the same unitary. But in the other case, when you have independent unitaries every time, you're basically just getting a uniform probability distribution. So these two are different, but it's very hard to find their difference if you don't measure the system exponentially many times, because the measurement outputs are almost not overlapping. Like you measure it, you get some bit string, and then there's 2 to the L of them. So if you are measuring like sub exponential times, with a high chance these bit strings you get every time are just different. So and you can show that these different bit strings all appear in the same probability if you have a random unitary. So of course there's no way to tell that from a uniform distribution. Yeah, so that's just the intuition why it's hard, like to distinguish the same unitary versus different unitaries every time. But we don't just prove it in that case. We prove it in the most general incoherent access QUALM, and so I'm going to only sketch the basic ideas of the proof. But maybe before that, I want to see if the problem itself is clear, like if the goal, like what we are trying to prove, is that clear? Okay, so I will sketch the idea of this proof. So basically the first step is to show that in the general incoherent access QUALM, you're doing multiple rounds of communication. So you do a measurement and send the result to W and then apply a channel to W. and you measure W. So then you send the result to L and apply a channel to L. This is just the most general form of LOCC, except that we require there is this complete measurement. So you have these multiple rounds of communications, but then we can prove that basically you can just consolidate all of them together, and that's equivalent to the simpler picture on the right side, which is with only one measurement. But the one measurement is not just the measurement in the orthogonal basis. It's a POVM. It's like you measure in some pure state Y with some probability lambda, and then so we are not showing that a general QUALM is equivalent to a particular simpler one, which we call simple measurement QUALM. It's actually equal to an average of them. And the idea is that, like in all these rounds where you apply some measurements to W and then send the results to L and then apply a quantum channel there, that's like a probabilistic instruction. Like based on the state of W, my computer, I give you an instruction, but that's probabilistic. It could be flip the spin or not flipping the spin of the L with some probability. But the point is that since we have access to the whole L, to the whole W, then all these probabilistic instructions you can do in a deterministic way, which means like you can do it with a classical computer. Like you can instead of generating that probability by measuring the quantum state of W, you can throw a coin and achieve the same probability distribution. So so the point is that you could just replace that instruction by a deterministic one, and then you and then in the end, so after you do that, in the end you average over the choice. Because like every step when you see an arrow going from right to left, you throw a coin and then determine the results based on the coin flip. And then in the end, you get a different algorithm every time when you get different coin values. But after averaging over them, you get the same QUALM as before. But for each particular value, then you have these deterministic instructions. So now they are just some gates applying to W. So the only thing you're doing is you measure L and then you read the results. So once you do that, then you can just merge all the different measurements and then show that they are equivalent to the single measurement. So there is this single measurement QUALM, simple measurement QUALM, where you do this POVM, where you take the state. The only thing you do after you apply lab oracle is you take the state you get and then project it to this basis Y. But there's a POVM because there is a weight factor lambda. Like you don't just get this probability, but you get the probability of this times lambda, and then you prepare a new state sigma that and then feed that to the next round. Okay, so that's what you do, and then in the end, you just get the measurement results of every step, like S0, S1, S2, S. And then the output of W is the probability distribution of them. And then you're trying to distinguish for these two lab oracles, the two probability distributions. So the thing we prove is that when this K is smaller than that exponential upper bound, then the difference between the two probability distributions in one norm is smaller than K cubed over the dimension of Hilbert space to the L. Yeah, so that proof itself is technical. I thought that since this is a quantum information seminar, maybe I will show a little bit of that proof. The proof itself, so far, we have shown that how the general QUALM is reduced to the simple measurement. And then for the simple measurement, the proof is some math, but I will sketch it here. So basically, because every step you do the measurement, so the probability distribution you get is just a product of these probabilities. Of every step you do this measurement, you get this probability that's a matrix element like this. But the non-trivial thing is that you're allowed to have adaptive algorithm, which means these states, like the measurement state Y, they depend on the previous steps. That's why I have these indices in the lower indices, because like you could be measuring the spin x in the first time, and then depending on the result, you could decide I'm measuring y next time, or I'm measuring z. So you can't view them as independent measurements. Every time I'm doing a different measurement, and then but the probability is a product of these kind of matrix elements, which I draw here. So you basically are applying the sigma is the state you prepared, and then you apply the lab oracle u, and then you measure it. And so that's what you get here. And then if you average over u, you can use these Weingarten functions and reduce that into a product, like a sum over the permutation, sum over a pair of permutations, and then one permutation applies to the sigma, the other permutation applies to the state y. And then once you do that, then you want to bound these contribution of non-trivial permutations. So basically, it's relatively easy to show that if you take the permutation tau to be trivial and sum over sigma, and that part gives you basically the same as independent unitary, like give you the same result as if every unitary is separately random, then you just get a uniform distribution. So that's what you get. That's approximately what you get, plus some subleading corrections in dimension. That for tau is trivial, and then the non-trivial tau is what you want to bound. And then here for the non-trivial tau, basically you can just, I mean, the picture on the left side is trace of sigma with permutation. The trace of the state, oh sorry, I realized I used the same label for the state and the permutation. It's called sigma. But so the state you prepared traced with the permutations, that's always smaller or equal to 1. So you can just get rid of that, and then you just get some sum over non-trivial permutations acting on the state y. And that's the thing that we bound with this very simple inequality. Like the y is just a permutation. So it's like you have the different states. So the different triangles here are different states. You have these matrix elements which are overlapped between these different states, and then you bound that by some squares of some part of them. And then there is a key thing that you need to make a clever choice of the separation. Like this is a product of 4 terms. I can make it smaller or equal to square of the 3 and 1 or 2 and 2. But because the measurements are adaptive, so the states later, like in the later measurements, could depend on the things on the earlier measurements. So you need to keep that in mind. Like they are not just independent things being summed. So after we carefully taking care of that, we can show that you can always find a decomposition so that this adaptiveness is not a problem. So you do a sum over these basis states from the future to the past, and in the end you prove that this contribution from non-trivial permutations is of order k cubed over d and k squared over d and other things. And the k cubed over d and k squared over d are basically contributions from cycle 3. Like cyclic permutation of 3 elements and 2 elements, I think. Anyway, so basically, yeah. So that's all I want to say about the proof. But basically, so coming back to the result itself, it shows us that if you don't access the system exponentially many times, it's very hard to it's impossible to tell the two situations apart. Like to tell whether you're applying a new random unitary every time or the same unitary every time. And because of that, so we can have other corollaries based on this main theorem. So if it's very hard, for the first one is the unitary ensemble distinction. It means that if you can't distinguish the same unitary every time with a new random unitary every time, then you basically can't distinguish anything in between. So if you consider a different lab oracle, it's like a Brownian circuit, but it's not entirely random. Like you have a Hamiltonian with some random parameters, but not entirely random. So then, so if you consider an ensemble of unitaries that they are correlated, they are not independent, but they satisfy this invariance. It means that if you multiply the same unitary on the left of everything, then the probability is the same. So like you could, so this included like the case where you're always applying the same unitary every time, but the same unitary is hard random. And the other extreme is like they are all totally independent. Each of them is hard random. But there's many things in between. Like you could have a use with a correlation in time. But as long as, say, the first one is random, then basically the whole probability distribution is uniform when you multiply all the unitaries from the left. So you can show that these are all very hard to distinguish from the trivial case where every time is the same random, every time is independent random unitary. It's basically because they are something between these two extreme limits. So we can make use of the two extreme limits to show that it's very hard to distinguish this case. So the other corollary is about state distinction, and that's not surprising that if you can't distinguish this whether these unitaries are the same, you can ask a similar question for states. It's like if I have a lab oracle that generates random states, but there are two different lab oracles. One is generating the same state every time. The other is generating the random state every time, a new random state. Then we cannot distinguish them, because if we could, then we could use that to distinguish the unitary. Right? So we could just apply the reference state, apply the unitaries to the reference state, and then distinguish them. So our theorem implies that you can't distinguish these two ways of generating states, and also you can also generalize that to this joint probability distribution. It means that you cannot distinguish different ensembles of states as long as the probability distribution is left invariant. The invariant under multiplying the same unitary every time. So other than these corollaries, there is a case that has more physical interpretation, which, I mean, you could also call it a corollary of that problem, although it's a little more non-trivial. We need to do some more proofs to get that. But so the concept, this is the symmetry distinction problem. So we want, there's a physically we know it's very important to identify symmetry of a physical system, whether something is time reversal breaking or time reversal invariant, or parity breaking or parity invariant. That's a physical question that we are always very interested in. So we study a toy model of that. We say, let's consider that Floquet system, which has the toy model that every time you call the lab oracle, you are applying the same unitary. So that's like our toy model for Floquet system. But now we can consider three different cases which are different by the symmetry. So the first one, LOU, is like applying unitary, a hard random unitary every time, and it's the same unitary. The second one is applying the same orthogonal matrix every time, and the third one is applying a symplectic matrix. So yeah, so it's just three different ensembles of with different different symmetry classes. So then the question is, okay, so can we distinguish these three cases and doing some measurements and tell them apart? And then with coherence, you can do that easily. And the reason is that there's some nice trick that we know how to, but making use of the entanglement, we know how to apply the transpose of the operators. So that's so basically you apply the lab oracle, and then here we call it A, and then you can do a swap so that A now is applied to this W1, and then you apply another A to the swapped in system. So basically, so after you do this, you get like A applied to this qubit and A applied to that qubit. But if you prepare the system in the correct entangled initial state, that's the same as applying A transpose to one of them. Right? So you apply the operator A on a qubit is the same as applying A transpose to its partner if they are maximally entangled. So that's why it's very different for unitaries and orthogonals. And when you apply unitary, UU transpose is non-trivial, but when you have orthogonal, it's an identity operation. So you can just take another pair and then just compare them. If they're the same, it's orthogonal. If they're not the same, then it could be one of the other two cases. And then you can distinguish the other two cases because there is a similar condition for the symplectic class. You just need to apply that symplectic J, which is like sigma Y. You just need to remember to apply that, but there is a similar condition involving transpose, which you can make use of. And the unitary ensemble just have nothing like that. Yeah, so this is how you can distinguish the three cases using coherent access to your system. But without a coherent access, it's very hard. And we basically just follow the proof in the exactly the parallel in the unitary case, which we shown earlier. You just follow that kind of proof and show that all three cases are indistinguishable from the Brownian case, where every time you are applying the same unitary or orthogonal. And in that case, it doesn't matter whether you're applying one of the three classes. You just get a uniform distribution. So since we have shown that all three are indistinguishable from that trivial case, then they also cannot distinguish from each other. And the way you prove them is the same using Wien-Gardner functions, just the inequalities of Wien-Gardner functions are a little different. Yeah, so okay, so I think that's the that's my the main message in this talk. So in summary, I think there are two purposes of this work. One is we set up this framework so that we can describe a general quantum experiment and define complexity. And the other part of the work is to have this specific problem that we use as an example of this exponential advantage. So we show that in this particular toy model where you want to distinguish the fixed unitary versus a new random unitary every time. I mean, you want to distinguish Floquet versus Brownian, then this is a task that's easy with quantum coherence, and it's very hard with incoherent access. And then there's, as a consequence of that proof, we can also study the other physically relevant problem, which is distinguishing between different symmetries. And yeah, so I think this is the first this kind of exponential advantage in a physically motivated problem. After finishing the paper, we learned that there are two other examples in recent years from very different contexts. So yeah, but it's quite different from the Simon's algorithm because entanglement plays an essential role here. Yeah, so I think there's a lot of open questions about how do we find some more realistic problems and then study them in this framework. And there's other questions like how do you include noise and pseudo randomness and so on. Okay, I will end here. Yeah, thanks.